Hi, today I'm going to talk about how to connect the encoder of your brushed DC motor to Solo to be able to control the speed and position of a DC brush motor. To control the torque of a DC brush motor, you actually don't need to have any encoder or any other sensors. You can always do it in sensorless. But if you want to do an accurate speed or position controlling like servo driving a DC brush motor, you're going to need to connect an encoder to it. Solo supports incremental encoders for DC brush motors, and today we're going to learn how to connect properly the wirings of the encoder and the wirings of the motor to the outputs of Solo. So to start that, there are two phases in this tutorial. The first phase is to find the proper wiring for the encoder, and we will start from that part. Then we're going to proceed to the next part, which is connection of the motor wires. So for the first phase, I don't need to connect the motor, I just need to connect the encoder wires. Your encoder wires probably has 5 wires. 2 wires are for supplying a +5 volt and a ground. You need to know those 2 pins because they are crucial, and 3 other pins which are known as A, B, and index. To control the position or the speed of a DC brushed motor, despite 3-phase motors, you do not need to have the index pulse connected. This is the case in this tutorial because my motor doesn't have the index pulse, my DC brushed motor. But the index pulse is important to use for 3-phase motors. But since this is not a 3-phase motor, it's a brushed motor, brushed DC motor, I don't need the index pulse, I just need the A and B pulses of the encoder connected to Solo. So you can connect those pins in an arbitrary fashion in the beginning, I mean the A and B, and then here in motion terminal we're gonna verify if those connections are right. So I have connected my wirings of the encoder properly, and I'm gonna connect it to the encoder input of Solo. So once I put it there, I would be able to go to the motion terminal and see what's happening. Now I need to go to the motion terminal. Before that I turn on Solo. So once the LED E2 starts to blink, it means everything is okay. Now I can go and get connected to my Solo. So you see that here, this is the default condition of Solo. Before proceeding any further, I need to make sure for the first phase, I have selected the motor type also on the piano switch. So I'm gonna select the DC brushed, which means I have to press pin 1 and 2 down. So this means that I have selected in analog mode, the DC brushed mode 2. It's true that now we want to use the digital control in Solo. It's always good to have the same motor selected on piano switch in analog or digital, just to avoid any confusion. So I'm in the motion terminal, I read all the parameters. You see that since now in analog mode, when I read all the parameters, I read the DC motor, but maybe the motor in digital mode is different. So to make sure it's not that case, I set also here the DC mode and I read and I see it's okay. So now, this is the first parameter that you need to make sure that it's correct, the type of the motor. Then I need to set a proper current limit for my motor. For this type of motor, something like 10 amps is fine. The number of poles is not for DC brushed motor, so I'm gonna skip it. The switching frequency is okay, 20 kHz for this motor is fine. The next thing you need to change, it's the encoder lines. This is actually the physical encoder lines engraved on the disc of your encoder. So in my case, for this motor, it's 500 lines, and this is pulse per revolution and pre-quad. So it means that this is just the number of pulses on one of those lines of A and B. So it's 500 lines, but Solo operates in quadrature mode, so it will count actually 4 times more than this value when it turns 1 round. But here you have to only put the physical number of lines, which is 500 in my case. Once I do these things in configuration, I do not to do anything else, and I can immediately go down. I need to make sure in this section the control mode is on using encoders, because now I'm using encoders, and just to make sure I read it back and it seems fine. We have it there, and now I'm going to just let the position remain, and I'm going to remove the other parameters because I'm not interested. If I let the monitoring mode in performance mode goes on, and I turn the motor in counterclockwise by hand, you see that the pulses are rising up. This is a good sign. This shows that the A and B are connected rightly, and if I turn the motor in clockwise direction, I see the number of pulses are going down. So this is the condition that you need to verify that is happening. If it's not happening, you need to swap A and B because maybe in your case, once you turn the motor in counterclockwise, instead of going up, the position is going down. So you have to swap A and B. So you need to see the plot going up while you turn the motor by hand in counterclockwise, and going down when you turn the motor by hand in clockwise. This is the first phase, and I verified that it's okay in my motor. Now I'm going to find the best wiring for the motor. For now, in the second phase of this test and tutorial, I'm going to let solo to be in open loop. So I'm going to leave pin number 5 up, but after a little bit we go forward, we need to go to closed loop, because closed loop is actually what we are interested in. But for now, to do a little test, I'm going to let it to be in open loop mode, and then at the end of this tutorial I'm going to put it in closed loop, and we are going to test the speed and position. So for now, let the pin number 5 stays up. I'm going to connect the motor's wiring to B and C outputs of Solo, which is for DC brushed motors, if you have DC brushed motors. But I don't know which combination is actually the right combination, so I'm going to just connect in an arbitrary manner the black to B and the red to C, and see what happens. And then we're going to find the correct wiring for this inside the motion terminal, and if we need, we might need to swap the wires. So now I'm going to find the correct wirings for the motor. Before that I turn on Solo, I go back into motion terminal, I get connected to my Solo again, and I do not need to change anything here. Everything I'm going to do is here. What you need to do is this. First, to find out the correct wiring of the motor, I put back Solo into sensorless mode, so ignoring that the encoder is connected just for this little part in our tutorial, I'm going to go into digital mode and speed mode. So since the motor is in open loop, the gains of the speed controller doesn't make any sense. I just need to put here a value which is defining for me the open loop duty cycle of Solo at the output. So if you look at the datasheet of Solo, you see that this value, it can be something between 0 to 30,000, which will map from 0% to 100% if you are in open loop. So if I put this value like something like 3,000, it means that I want 10% duty cycle on the output of Solo in open loop. This is not in RPM, because in open loop, actually RPM doesn't mean, it's just in terms of duty cycle. When we go in closed loop, this will have its meaning in RPM. So I put 3000, and I'm gonna see that my motor now, it's in clockwise, it's set to work in clockwise mode. I'm gonna ask it to go for 10% of duty cycle. What I'm expecting to see is the motor turning in clockwise direction. And if it turns in counterclockwise direction, it means that the wirings here are not correct. So I put 3000, I'm expecting my motor to turn in clockwise direction if it's correctly connected. So I go and I see the motor is turning in clockwise. If I reduce the duty cycle, for example, like something less, you see that it's turning in clockwise direction. I can go even less than that. So this is kind of an indication that the motor is going into right direction. So this means that my wiring is correct here, because if I was seeing this motor now is turning reverse in counterclockwise direction, I had to swap these two wires together. So now my motor is connected properly. I stop the motor. I don't need to work with the motor. Now I need to go into closed loop mode. So while Solo is on, to do the motor identification, if you press pin number 5 down, you see that the motor will vibrate for a little bit. We went into closed loop, and closed loop is what we are interested in. So if I read all the parameters again, I have now the current controller gains totally ready and tuned for me. I can run again the motor identification from here, but since I did it here, I don't need it. But if you want, you can run it again, and you see that the motor will vibrate a little bit. It doesn't matter to run it again. You do not need to do any encoder calibration for DC brushed motor. So this part, it doesn't make any sense. Now we actually want to use Solo in encoder mode. So I go back into encoder mode, because I went to sensor mode just to see if the connection of the motor is correct. From now on, we stay in encoder mode, and I'm gonna go in a speed mode. I was there, so in digital speed, and I set 2 gains for the speed controller. For me now, I found these 2 gains that are working well with this motor. And Now it's the time to set a reference speed. But before that, I'm gonna let the motion terminal performance monitoring runs for itself. I'm not interested in position. I'm not interested in angle, because this is for brushes. I just want to see the speed and torque and see what happens. So if I ask the motor to go to 1000 RPM, it went very nicely, and you see that the motor went all the way up to 1000 RPM, and you see that the red plot is the step response of the speed. Very nicely went up, a little bit of overshoot, and then came back on 1000 RPM. And then this is the torque, IM. Once you're in DC motor, IM is actually your torque. So you see that the current is actually something like around -1 amps in steady state, and that's it. Now I can play a little bit more. I let the monitoring mode going on for itself. I stop the motor. Maybe I ask for 3000 RPM. You see that here, the plot is very beautifully drawn. I change the direction abruptly, and the direction of the current changed. The speed went back again in other direction, 3000 RPM. I stop the motor. So it seems that my speed controller works fairly good. Now it's the time to tune the position controller. I've already checked the speed controller. It's working. So what I need to do is this. I need to go to position mode. I need to make sure that my position is okay. So as you see, my initial position now is at something non-zero. If I put now the position controller KP gain, the motor will try to reach to 0 because the reference now is set at 0. This is not good. To avoid that, because now we are in testing phase, we already tested the speed mode, the motor turned a lot of turns, and that caused the position to change. But in a normal condition, you do not do that. If you're in position mode, you turn on the system, you start from 0. Or you can do your own homing algorithm, but for now, to avoid that, I turn off solo to reset everything. I come back again because I just want to test the position controller. I don't want to have any effect from the speed or torque loops. So when I come back again, I need to go to digital mode again, and in position mode, I have the gains already set for the speed controller. I just need to put my gains for position. And before that, if you read the number of pulses that you counted from the beginning, it's actually almost 0. And I just put the gain for position controller KP that I know it's fine for this motor, and the gain for position controller KI. So now it's the time to see the quality of position controlling. Before that, I'm gonna let the monitoring mode goes on. So I let the position, the current side of the DC motor or the torque of the DC motor, and the speed remains visible. So I go up, and before I set the desired position, here you need to define the speed for your trajectory. So 30,000 RPM is absolutely too much for this motor. I'm gonna go for 2000 RPM. It means that I'm gonna follow the trajectory, the goal that I put here in desired position with this speed. This speed can be changed dynamically as well as the desired position. For now, I'm gonna ask Solo to go to positive 100,000 pulses, and let's see what happens. So if I send this, I see that the position rose very nicely from almost 0 to the goal that I asked. There is a little bit of error that you can, of course, tackle the error by changing or increasing or decreasing these values for position control KI, position control KP, or even speed control KP and KI. You can play more, you can find the best gains, but at the end of the day, this is a nice plot for you to have. So it means that you see that the speed after reaching to the goal stayed steady, and then the position arrived. Now to see a better plot, maybe we can zoom a little bit out, and I this time give -1 million pulses, quadrature pulses, and see what happens here. So it's going down, the speed is fixed, the torque is fixed. If I apply some load on the shaft, there will be some little disturbances, which I can enhance the behavior of the system by tuning the gains better and better. So you see that, for example, we have a relatively big overshoot here because probably this is due to the gains of the speed controller. I can reduce that overshoot after releasing the torque, but you see that the controller tries to keep the speed steady at 2000 RPM. To achieve the best tuning, you need to find the best gains for your current controller, speed controller and position controller. But for a fast test, we could achieve the good test. So you see that now here, for example, we are at minus 1,100,000 pulses. So there is a little bit of error. If I increase the position controller KI, I'm expecting to have less error. So that was how to tune and make sure that your DC brushed motor is properly connected to the Solo in terms of the connection of the motor's wires and the encoder. Then after this, you can switch back to the tunings. You can find the best parameters for your motor for the position and the speed and torque. Thank you so much. Please subscribe to our channel. We will provide you more materials in near future. See you soon.